Howdy. The purpose of this video is to talk about the heat capacity of materials. Now, what is the heat capacity? Heat capacity is the amount of energy that it takes to change the temperature by some set amount. So it turns out that if we look at different materials, let's think about silver, lead, and aluminum. And if I put in the same amount of heat in each of these cases, let's say 1 joule of heat, then I would see the temperature rise in all three metals, but it would rise by different amounts. And that difference in the change in temperature is given by the heat capacity. If we think about it differently, temperature is a relative scale. It's telling us what is the average kinetic energy of the molecules in a substance. So if I have two things that are at different temperatures, I know heat will flow from the higher temperature to the lower temperature system. Heat is energy. Heat is an absolute quantity. If you remember, energy can neither be created nor destroyed, right? It can only be changed. So if we're putting energy in, the total energy, the total heat of these different materials is changing by the same amount. But the temperature, the amount of this relative kinetic energy scale is different. And that's what the heat capacity tells us. So again, the definition of heat capacity is the amount of heat that it takes for some designated temperature change. So usually I think about how much heat does it take to raise the temperature by 1 degree Kelvin. And we call that term the heat capacity. Oftentimes we would talk about a constant pressure or constant volume heat capacity dependent on the conditions of the experiment. So every material has some heat capacity. Now, what affects heat capacity on the material level? And even more importantly, where is that heat being stored, right? So the largest contribution to heat capacity is lattice vibrations. As I keep heating up a material, the lattice can vibrate more and more and in different directions. So this gives rise to a very interesting phenomenon, right? Because if I think about a system at a very low temperature, if it's at a low enough temperature, then I don't have enough energy to access the different vibrational modes, right? Phonons, we talked about phonons in a previous video, but just as a reminder, phonons are quantized lattice vibrations. So they each have some energy associated with them. So the material has to start warming up before I can access some of these different vibrations. So at very low temperatures, the heat capacity of materials always goes to zero. It goes to a negligible amount. And that's because I don't have enough temperature to start accessing the different phonon modes, the different vibrational, the different vibrations that I can access in a real material. As I continue heating a material up further and further, at some point I'm going to be able to access all of these different vibrational states. And so what you see in different materials, if we're only looking at the lattice contribution to heat capacity, all materials will asymptote out to the same value. And that value is given by 3NK, or alternatively 3R. So R is the ideal gas constant, K is Boltzmann's constant, and N is Avogadro's number. So the heat capacity is ultimately a function of how many atoms are there in the material. And this is why different materials are going to have different heat capacities, because usually we think of a kilogram of a material, and we would give a specific heat capacity, so heat capacity per unit mass. In that case, 1 kilogram of lead is going to have a lot fewer atoms than 1 kilogram of aluminum, say. So they would have different specific heat capacities. But on the atomic or on the molar basis, the heat capacity for all these substances is going to approximate 3R at high temperatures. So what do I mean by high temperatures? Well, each material has a different what we call the Debye temperature. So the Debye temperature is a temperature, it's right about here. It's given on 1 because I've normalized this axis here. But the Debye temperature is the temperature at which I'm able to access most of these vibrational modes. So by the time I get to the Debye temperature, the heat capacity is almost constant for all these different materials. So let's think about a different way to plot this graph. Instead of normalizing, let's just plot it on a traditional temperature scale. So if I'm plotting heat capacity versus temperature for a number of different materials, some materials I would see a relatively low Debye temperature. So T sub D would be relatively low on this material. Another material, I might see a relatively higher Debye temperature. So it's somewhere out here. But they're all asymptoting to the same value. And if I collapse, if I renormalize by the Debye temperature, then I actually see quite good correspondence between different materials on this kind of a chart. So I could plot it up and I could see metals, and I could see semiconductors, and I could see ionic materials, and they all would tend to follow this same universal curve. And so it's really interesting, right? The heat capacity is not really a function of what the atoms are at all. It's mostly a function of how many atoms we have. The one exception is that the Debye temperature varies for different materials. Okay, so in summary, we talked about a definition of heat capacity. How much heat or energy does it take to raise the temperature by 1 degree? Heat is primarily stored through lattice vibrations. There are other mechanisms, but they're usually relatively minor. And a couple things to remember is that heat capacity goes to 0 as temperature goes to 0. That's because we don't have enough energy to excite these thermal vibrations. And heat capacity goes to some uniform value as temperature increases and increases. And that's because at some high temperature, we've excited all the vibrational modes that are possible in that given solid material.